Okay, so for internal forces, they're actually very similar to the concept behind why we did frames, right? Because frames, we pulled the pins and found what was happening inside of it to prevent it from coming apart. Internal forces is very similar, but now we're looking at what's happening inside of a member, right? So this is an arbitrary problem I just came up with because it had a couple of things that I wanted to talk about real quick, but the numbers might not add up. So we'll see. Um, what happened was basically internal forces, like I said, is the force happening inside of the member that keeps it from breaking, moving, snapping, twisting, anything of any kind of motion. Um, So the first step in all of these problems is to solve or draw a free body diagram of the entire system, right? So you'll be given a problem, but it's still going to have like all the supports on it. Like for example, this one would still have the the roller and the pin here. So my recommendation would be first off is to draw all of the free body diagram stuff for the whole system. And I forgot my little thing. So after you've done that, it'll ask you in the problem to cut the member at a certain point here in the problem. And that I just drew, I'm gonna cut it at E, right? So cut the member at point E to expose the internal forces at that point. Well, what are the internal forces, right? First, there's a shear force, which goes along the face of the cut, right? And that is basically preventing the member from snapping. So if I had force here and on the other side a force going up, it would want to create some kind of like frictiony kind of cut here, right? It'll essentially want to shear the member, right? So the shear force is the force that's built into the cut itself parallel to the surface that prevents the member from shearing, right? Similarly, the normal force is the force inside of the member that keeps it from being pulled apart or pushed together. So essentially, if I was going to take the example I used in class was a pool noodle. If I was going to take that pool noodle and pull it apart, there's something inside of that pool noodle that's keeping it together, right? So that's a normal force. And just like you would think, it is perpendicular to the surface that it's acting on. So the last one is the moment, right? So if I was going to twist the pool noodle, right, like pull, rotate one side towards me, one side away from me, there's some force inside of that pool noodle keeping me from breaking it when that happens. But in statics, again, it keeps it from moving. So basically, every time you cut a member, you expose all three of these forces. And because you expose all three, you have to make sure that those are the only three unknowns you have in your body at that time. So here's the cut that I made, right? I made it at point E. Um, and here are my internal forces, right? At point E. One thing to remember is that you include all three forces on both sides of the cut and they're equal in magnitude but opposite in direction, right? Because if I put these back together, I want them to cancel out entirely because they're internal. If they didn't cancel out, they would have some sort of external effect. The direction doesn't matter in terms of which one. So, like I drew, for example, I drew this one first, and I always draw it in the positive direction. So first I drew V up and to the right and M clockwise. And then everything else on the other one, like I drew this one next, I drew everything in the negative direction. It doesn't really matter, just something that I usually do. I don't know why or how I picked it up, but that's what I do. Another thing I wanted to bring up is if you're cutting a member at a point where there's a distributed load, you cut through the distributed load too. So remember up here, E was like kind of in this awkward, like almost middle point of that distributed load. So I had to separate the distributed load as well. So that's what I did. Moving on, you only have to solve one side because they are equal in magnitude, right? So you choose one side and solve for it, right? The goal is to make this easier for yourself. So, I personally choose a side that's shorter, or if there's a side that has fewer forces on it, or say I was cutting it at like this point here, I would probably choose this side because it doesn't have a distributed load on it. I mean, it doesn't really matter which side you choose at the end of the day, but I usually choose one that seems like it'll be easier for me to do. And then you draw the free body diagram for that like smaller chunk again. And if there is a distributed load, consolidate it into one point force. And remember, that's just the area of the shape that it's formed at, that it forms. And then it's located at the centroid of that shape. So really, if I was drawing this accurately, I would scoot it over to here, 4 kilonewtons. So then if I was going to solve this, I would I would essentially use this free body diagram here into my equilibrium equations, right? Because I have one unknown in each direction, so it should just be one iteration of the equation. So some of the forces in the x direction, the only one I had was my normal force. So that one is 0. Some of the forces in the y direction, I have 5 kilonewtons at the support minus 4 kilonewton of load. That's 1 kilonewton down on this member, right? Which is ED or DE, doesn't matter. The moment equation, I want to take it about the point that is not my cut, right? Because I don't want to cancel out I don't want to cancel out that one moment there. So by taking it about the other point, I can include the moment in the equation. So 0 equals this 4 newtons, and this is supposed to be a 3. I might have goofed on this math. I definitely goofed on this math. So this is a 3 kilonewton, or 3 meters, because it's 3 meters from point D. And then that would be 12. And then times the shear force, right? Because if I'm looking away from D, this force would be in that equation times the 3 meters that it is away. And I goofed again on this math because it's 3 meters long. It's happening halfway through the 2 meters there. So this would be a 2. So then you would end up with, because this 4 meters here is at the halfway point of that. So it would be 1 meter here plus 1 meter here would be 2 meters. And then you simply solve. So that would end up being 5, because it's 8 minus 3, so 5 kilonewtons counterclockwise on DE. And that looks like my final answer. And then the important thing to remember, just like in pins or in frames where we found the internal forces in pins, these forces show up on both sides of the cut, right? So my shear force was on both sides, my normal force was on both sides, and my moment was on both sides, right? So because it shows up on both sides of the cut, I have to identify which cut I'm looking at, or else my direction could be like interpreted multiple ways. Other than that, that's frames. We're gonna get into more practice problems, obviously, in frames too. So I might post a follow-up video depending on how the class goes. But here's at least an intro video.